Composites. I am Ananya and I'm a PhD student at IIT Delhi. So this is the extra class for this lecture series of aluminum based alloys and metal matrix composite. Our last class will be on 17th, which will be on the doubt clearing for week 12, but this class is a type of recapitulate class. So if you have any doubt from all over the course content, please let me know. Otherwise, you tell me, how should I proceed? Should I start with one by one all the topics from week 1 or some specific topic to rediscuss?
Ma'am, from my viewpoint, you should recapitulate all the points, and then suppose if we get doubt or we are stuck somewhere, we will ask you to discuss it
Okay,
further.
okay.
Oh yeah, mom, that will be fine for me.
So we'll start with all the topics from week 1. I don't have any PPT today. So first, the very basic of aluminium was discussed, that what are the properties of aluminium, like density, melting point, boiling point. Boiling point is not that much important, but uh, the melting point is very important. It's 660 or 659 degrees centigrade. Always remember if you are working in aluminium. Also the density, which is 2.7 gram per cc. Then the thermal conductivity, electrical resistivity, those things. It's a non-magnetic material. It's also important. So aluminium is having the ductile nature. It is having FCC type of crystal. So in FCC, there are a lot of slip plane. So it can easily have the dislocation movement inside the material. So it's FCC in nature. Then we had a comment like, if we mix the alloying element, we basically reduce the ductility. So alloying is done to reduce the ductility by adding some alloying element. That those elements can be copper, silicon, magnesium, chromium, manganese, zinc, lithium, etc., etc. So then we were discussing about the extraction of aluminium from bauxite. So bauxite is the main ore of aluminium, which consists of gibbsite and dispore. And gibbsite is Al2O3 3H2O. Dispore is Al2O3 1H2O. Then from these two components, we basically extract the Al2O3 by which process? Can you recall?
Bayer's process.
Yes, Bayer's process. After that, we go for Hall-Héroult process. In Hall-Héroult process, uh, we extract the aluminium and hydrous aluminium from the Al2O3 or alumina. So alumina is a very stable oxide. So when the 2000 degree centigrade is increased at the time of carbothermic reaction, so it's practically not viable because of the stability of aluminium. It cannot, means the refractory element or lining which is needed for the electrolysis of this thing cannot sustain that high temperature. So that's why aluminum will form some aluminum carbide, so Al2O3. So that's why carbothermic reaction was not possible. So then Bayer's process was discussed. For the sake of knowledge, you can remember the Bayer's process, the Hall-Héroult process, Exam point of view, it's important, but if you're working with aluminum alloys or metal matrix composite, it's not that much important to remember always, but for exam you have to remember these things. So I'm not going into those extraction process. Rather, I'll talk about the other things, like there can be sources of the impurities that can be mixed up with the aluminum. The sources can be like the bauxite ore that you are taking, the refractory lining that you are providing, the electrodes, cathode anodes, and the crucible where the aluminum will be melted, the tools that you will be using. At that high temperature, it can secrete some elements, and these all things can add some impurity to the process. So whatever aluminum we get it like 99.9 something percent, and it's not 100% because of those impurities, but it can be super or ultra pure aluminum as well. When the aluminum, it will be ultra pure, or it will be called as ultra pure aluminum when the aluminum percentage is 99.999 percentage. Other than that, there were high pure, super pure, extreme pure aluminum. After that, the next topic started, which is the aluminum alloys. So aluminum alloys are designated by two names. One is cast alloy, another one is wrought alloy. Cast alloys are not that much used in case of metal processing applications. Wrought alloys are used which are the 1000 series. Cast alloys are the 100 series. Cast alloys are named as 1, 2, 3, 4, 1 to 800 series, depending upon which alloying element is the main constituent. Always remember, all the type of aluminum alloys will have this alloying elements like copper, silicon, magnesium, manganese, zinc, lithium, sodium, whatever. But which constituent element is more in percentage, depending upon that, it is named as 2000 series or 3000 series or 4000 or so on, or 100 series, 200 series, or 3 or so on. So we were more concentrated about the 1000 series because those are the wrought alloys. We basically work with the wrought alloys, the working like welding or some additive manufacturing or the forming, forging. We go, or the machining, we go with the 1000 series because those are the wrought alloys. So then, before that, there was one topic of filtration. Uh, Means if some extra impurities are added, so we go for filtration. Different types of filtrations techniques were discussed, like gas purging to eliminate the gas, like hydrogen gas which is dissolved, because hydrogen can lead to embrittlement to the material or the aluminum, and there is chance if the aluminum is exposed to a hydrogen enriched environment, then there will be chance of getting dissolved, the hydrogen to get dissolved inside the aluminum, and it will lead to embrittlement of the matrix of the aluminum or the aluminum alloy or whatever. So we obviously always try to avoid the hydrogen to get it mixed with the aluminum alloy. Then there were other techniques also to eliminate the fluxes and those things. Next, the wrought alloys. In the wrought alloys also, these can be heat treatable or non-heat treatable, or in the cast alloys as well, non-heat treatable or heat treatable. So non-heat treatable means, so heat treatment mainly consists of the precipitation hardening in case of aluminum alloy. So we can achieve the, so why do we go for heat treatment? First tell me.
Ma'am, to form the precipitates.
To form the precipitate. And why do we want to form the precipitates?
Ma'am, there are basically four types of. strengthening mechanism. So one of the strengthening mechanism is precipitation hardening.
Yes, so basically we want to harden the material. Aluminum is a ductile material too, so it's not, it doesn't have that much strength. So because of the ductility, so to increase the strength, we go for the different treatments by which we can increase its strength, means hardness. So in which we can do the precipitation hardening, because aluminum doesn't have any significant phases, it doesn't change its phase. What only it can happen is the grain refinement. We know smaller grains gives us better strength, so grain refinement we can do, or we can do the precipitation hardening. So basically we do the heat treatments to achieve mainly these two things. So non-heat treatable means we cannot do the heat treatment to get these two results. Although even if the precipitates are not forming, the non-heat treatable alloys will form some clustering, may form some clustering of solute atoms to have that hardness. We may go for heat treatment, we may go for some treatment by which we can do the grain refinement, by which we can achieve that hardness. So it's not like we cannot go for the heat treatment, we can go for the heat treatment, but the precipitates will not be formed in case of non-heat treatable alloys. So that's why we generally work with the heat treatable alloys when we go for the material processing, heat and material interaction, those type of applications where heat will be interacting directly with the material. So what are the non-heat treatable alloys? Anyone remember? Or what are the heat treatable alloys?
Ma'am, the heat treatable alloys are basically the 2x series, the 6x series, and the 7x series.
Okay, 2x series, 2x, 6x, 7x, 8x also.
Yeah,
And
yes, ma'am.
non-heterable are 3, 4, 5, and 1 as well. 1 is the purest form of aluminum alloy, where the percentage of the alloying elements are very less. So obviously 1 is also non-heat treatable, no precipitates will be formed. Anyway, one the 1000 series cannot be hardened that much as well, because grain refinement what only we can do there. So yeah, these eight different thousand series are there. So for 1000 series there is no alloying element. For 2000 series it's copper. For 3000 series, it's manganese. For 4000 series is silicon. For 5000 it's magnesium. For 6000 it's magnesium and silicon. That's why the what is the precipitate which generally forms in case of 6000?
MG2.
Mg2Si.
Yes, Mg2Si. It's very well known. And for 8000 it's lithium. 9000 is not that much used. So these are the different 1000 series alloys. Then if you talk about the 100 series, then again 100 no alloying element, 200 is copper, 300 is silicon, magnesium, 400 is silicon, 500 is magnesium, 700 is zinc, and 800 is silicon. Sorry, I said structure. So then there was another phenomena that after 100 series there can be written as point O, or point 0 or point 1, which signifies for point O it's near net shape, and point 1 ingot, which has to be further processed to give a particular shape by some forming or forging process. Then some information about the silicon, because silicon is a very important constituent element for aluminum alloys. We know about the silicon growth. We know that silicon adds fluidity to aluminum, reduces the shrinkage and those advantages of using or mixing silicon to it. And also silicon, depending upon the silicon percentage, there are hypo or hyper-eutectic alloy or aluminum alloy. So hypo means the silicon percentage is lesser. In hyper, the silicon percentage is more and the amount is 12.6. So if the silicon percentage is less than 12.6, then it will be hypo, and if it's more than 12.6, then it will be hyperelectric aluminum alloy. And depending upon these percentages, the silicon growth, the precipitates, all those things will be formed. Because if it's hypereutectic, then the primary silicon amount is very high, and we know there is a phenomena related to Si, which is the uh, TR TRRE. What was the full form of TRRE? What was the full form? Twin, sorry, TPRE, not
Twin
TRRE.
plane,
It's TPRE.
twin plane
Yes,
current
it's
edge.
twin plane retrant edges. So what happens is, if there is a twin plane and the twin plane is 111, then in the direction of 111, there will be a huge silicon growth, uncontrollable growth. It will just replicate along with the direction from that twin plane, and it will grow. And we know silicon is a brittle structure. Silicon has a empty D shell which it can extend. Empty D shell which it can extend or expand, due to which it can form more than 4 bonds. Generally or ideally, it should make 4 bonds because of the 4 electrons in the valence shell. But as it has an empty D shell, it can expand its bond. So that's why it makes some mesh-like structure, and due to which it has a tendency to grow along with the twin plane boundary. So which is called as the growth of the silicon, which has to be restricted, otherwise we are using the aluminum for its ductility. If there is a lot of silicon present over there and the growth of the silicon is uncontrollable, that means the brittlity, a lot of brittlity will be added to the material, which we do not want. If we wanted brittlity, then we should have or could have opted for different materials other than aluminum. So if we have opted for aluminum, means we want that property of the aluminum. The most important property is the ductility. So we do not want this silicon to grow. So what we do, we mix some modifying element. This can be sodium, barium or strontium with 0.2%. This little amount of barium, sodium or strontium will act as a modifier to this silicon growth. So what it will do, the strontium will, or sodium barium, this modifier will change the growth of the silicon. If previously there was a twin plane like this, and if it was just growing like this, now this modifier is added. So this modifier will change the growth side. So if this is one, after some growth, the next growth will be somewhere else, and this is why the silicon, all the silicons present over there cannot grow after or beyond some certain limit, and due to which the brittlity can be controlled, the ductility can be maintained. Also, that we have restricted the growth of the silicon, and at the same time aluminum is having high thermal conductivity but lower latent heat of fusion than silicon. So whenever it is melted, at the time of solidification we are first mixing the strontium, first we are adding the modifiers, and then we are solidifying it. So what will happen, modifiers will restrict the growth, and at the time of solidification aluminum will solidify faster than silicon due to its properties like thermal conductivity and latent heat of fusion, and due to which the growth will be restricted, and the enhancement of the ductility can be done, or the ductility of the aluminum alloy can be maintained. So this was one phenomena. Then for wrought alloys, there are different designations. I'm not going into the designations because anyhow, whenever you are working with aluminium, you generally do not go with something like I'll choose, if I'm working with wrought alloy, suppose, so I have four digits or four numbers. I'll choose each of the numbers according to my choice, whatever I need. It doesn't happen. What happens is we generally go for the literature review. We see that depending upon our choice of application, what all materials has been used till date, we go for those aluminum alloys. Obviously, if we want to make some uh, specific product, I'll see what are the things to be used till date, what are the new aluminum alloys which are being used in that case according to the literature review. So that's about it, but you should know about the designation if you are working with a particular designated aluminum alloy, what is the significance of the four digit. Then comes the solid solution hardening. As I said in my last class also, that alloys mean, if this is the lattice in the corner of the cubes, the atoms are sitting. So this filled up are the alloying element. This is aluminum, this is silicon. Silicon is the alloying element, aluminum is the parent metal. So this will be the structure for the alloys, which is completely different for the metal matrix composite. I'm not going into that. So for alloys, as the solute atoms, this silicon will be called as solute atoms because number of silicon is lesser than aluminum, and we are mixing it properly so that all the silicons are mixed with the aluminum parent metal. So that's why it is called as solid solution. Is a kind of solution made up of some solute atoms and the solvent atoms, and it's solid, so it's solid solution. So solid solution को हम लोग harden कर रहे हैं, so we are hardening the solid solution by some typical way of alloying, means by just adding the alloy in first stage, by just adding the alloy we are hardening the solid solution. So by just adding the alloy means, uh, as an alloying element we can add silicon, magnesium, manganese, whatever we want, but the size of this alloying element can never be equal to aluminum. It can be almost like aluminum, like slightly lesser than, or it can be bigger than aluminum. Generally, the alloying elements which are being mixed with aluminum are having almost equal diameter like aluminum atom. So these atoms are substitutional. So for aluminum, the alloying is always substitutional, whereas for steel, where we mix alloying element to the iron metal, there it is interstitial. So substitutional means whatever I have shown here, it's a substitutional alloying. For aluminum, it's always like substitution. So just for mixing the alloying element, we are having some hardening effect. Like it can be elastic interaction, it can be modulus interaction, it can be electrical interaction, it can be for the stacking fault. These four things we got to know. So electrical interaction means one is, so electrical interaction means in, sorry, okay, just start with the electrical interaction. Means the,
Positive and the negative charges of the
yes. So means the alloying element that that I am mixing will have either lesser number of electrons in its atom or more number of electrons than aluminum. If it's having lesser number of electrons, it will be considered as a positive size. If it's more number of electrons, means it will be considered as a negative side in the aluminum. And according to that, a dipole moment will be created inside the metal or the metal alloy, in which what really happens at the time of hardening. So you guys tell me what happens now. What is the result of that dipole created? What happens? How we do harden the material? How do we do that? What is the main principle behind it? Try to recall it. It's very simple.
Ma'am, the dislocations form dipoles at their ends.
The dislocations.
Like they have dipoles, like they form, each dislocation forms a dipole.
No, no, not dislocations. Due to the alloying, we are having some dipole inside the material, because the alloying element will either have more number of electrons or lesser number of electrons than the aluminum. Then what will happen? It is related to the dislocation only. Just try to remember that what is the need of precipitation, what is the need of grain refinement, or not grain refine, what is the need of precipitation? What do you actually do by forming the precipitates?
Ma'am, like we hinder the movement of
Yes,
dislocations.
yes. So here also, as the dipole has been created, so the dislocations will either have a positive or a negative charge, depending upon which type of atom it is having. First of all, let's recall about the dislocation. If this is the lattice, then due to this extra half plane, the dislocation happens. So this extra half plane will be called as dislocation. So means dislocation also means a number of atoms which are bonded by one side, but on another side it's not bonded. There is no bonding in another side. It's an extra half plane. So that is what it will look like this then if dislocation forms. So this dislocation is also consisting of some atoms. So it can be either positive or negative. So if now a dipole moment has been created inside the parent metal, positive, negative, now this dislocation will sometimes get attracted to positive, sometimes it will go and attract to negative whenever it is moving. So due to the restriction in its path, it will feel some difficulty to move further inside the parent metal. This is how we do the hardening. The next way is elastic modulus, elastic interaction. Sorry. What is elastic interaction? If you recall, try to answer.
Ma'am, the solute atoms, they are more like they have more shear modulus as compared to the aluminium. So like
That one
uh,
is the modulus interaction.
oh, sorry.
You can open your note and tell me.
Mom, is it like the entire molecule can be, if there's a dislocation present, then the upper side of it could be compressive and tensile, so they could be giving a rather different type of interaction. So it is difficult for the dislocation to travel
Yes,
further.
it's basically if the alloying element is bigger than the aluminium, or the alloying element is smaller than the aluminium. Whatever it is, depending upon that, this elastic module interaction happens, because in this case it will get attracted, but it will not have the sufficient place. So there will be which type of force, compressive or tensile?
Uh, it will be tensile.
No, for bigger it's compressive.
Oh yeah, okay, okay.
Yes. For bigger, just try to remember this picture, that if it's bigger, then it will be compressive. It is spreading its arm, means it's bigger, so it will try to uh, push all the atoms present over there, but the atoms which are present over there cannot be pushed because they are having some definite lattice structure. So they will give a compressive force on this, and the total uh, the all over the lattice, it will they will the all over the lattice will feel that compressive force. So this is why for bigger particles it's compressive, for smaller particles it's tensile. Because for smaller particles, the aluminum alloys, surrounded aluminum alloys will try, aluminum atoms will try to get bonded with the small silicon, but the surrounding means, if this is, just look at this picture, then you will remember. Now this all things will try to get bonded with each other, but this alloying element, if this is silicon for example, this is smaller in size. So what will happen, it will try to attract all the atoms near it to get bonded, because it cannot extend its arm after some limit. So all the atoms will try to get closer to this uh, silicon, but the other atoms, aluminum atoms, which are present over there, will not let the aluminum atoms which is closer to silicon get bonded with them. So my picture is very bad, but it's like this. So what will happen? These atoms will try to get attached with the silicon, but these atoms will try to uh, means pull these atoms to make their bonding. Okay, so it will have the pull force, and these atoms are having some pushing pulling force towards the silicon. These atoms are having pulling force towards the silicon, and these atoms are pulling the aluminum atoms towards them. So the result will be a tensile force in all over the lattice. Whereas if this atom is bigger in size, this bigger atom will try to get fitted inside the lattice. So it will just push all the aluminiums present over there, but all the other aluminiums which are present over there in the lattice will not let this things pushed. So what will happen? These atoms are having a pushing effect away from the silicon, but these atoms are pushing the aluminiums away from them. As a result, this lattice will have a compressive stress. Is it understood?
Yes, ma'am.
Okay. So the elastic interaction tells us about the size difference of the alloying elements. And due to the size difference, there will be a compressive and shear tensile zone created inside a material, because not one alloying element but a lot of alloying element will be mixed inside the lattice. Some alloying element will be smaller, some will be bigger in size, and as a result this elastic interaction will happen, and due to which the dislocations will feel difficult to move further, because somewhere there is a tensile zone, somewhere there is a compressive zone, and it will be difficult for the dislocation to move further. The next is the modulus interaction. Due to the shear modulus difference between the alloying element and the parent metal, the dislocation will feel difficult to move. And the last one is the stacking fault. So who will tell me about the stacking fault effect, stacking fault interaction?
Ma'am, like the solute atoms, they do not allow the partial dislocations to come and join with each other. Like they increase the width.
So if there was one dislocation, now it has been broken down into two. And now if this position is favorable for the solute atoms, then it will come and sit over there, and it will not move until unless some external force is applied. And if the solute atom has sit over there, then the dislocation will further move difficult to move, will further feel difficult to move uh, forward. So this is how the restriction of the dislocation movement is done. And if there is restriction in dislocation movement, the hardening is done. So why we are considering that if the dislocation movement is hindered, the hardening is taking place. Why is it so? What is the relation between these things?
Ma'am,
Uh,
because yeah, okay, Vanshika, you proceed.
like actually, I wanted to say that if there is a flow of distributions, would help in deformation to be form a crack propagate. So if that is prevented, so hardness can be increased.
Yes. Before going into the crack also, if dislocation is moving inside the material, means the material is uh, engulfing the stress which has been applied externally. So means if there is an elongation, means the material is sustaining the force that has been applied externally, and elongation is attributed to the dislocation movement. So if we have restricted and also the elongation signifies the ductility, which is the lesser strength. If we have hindered the dislocation motion, then it will not get elongated, means that has been hardened, so the strength has increased. And this is what we want here, because aluminum is very much ductile material, which is not preferable for many applications. So the next one was the solid solution hardening part 2, where it was said that are if the atoms are arranged like this, so these are the alloying elements. Suppose this is B and this is A, then if this is the case, it's fine. But if due to the slip plane movement, dislocation movement means also the movement of the slip plane. So if one plane has been moved by 1 unit, 1 unit means this is the 1 unit. Now what will happen? The next position will be like this. and which will be a difficult position for the dislocation to move further, because the bond energy between this is much higher than the bond energy between this. Means the bond energy between same atoms are always higher than the bond energy between two different atoms. And this is why when this happens, this is called as antiphase boundary. It will take place in a short range and not in a long range, but across the lattice, if this has taken place, it can also be called as the super. When it is a long range, it will be called as superlattice. When it is a short range, in short range this can happen, and it will be called as APB, which is antiphase boundary. And APB is also very important in case of other type of strengthening as well. And if EPB has occurred, the dislocations will feel difficult to move further. This was the concept of next part. Then there is the atmosphere, concept of atmosphere. So what happens is the solute atoms are moving. So why we have added the solute atoms? Because of these four. ये चार तो है ही, उसके साथ there are other advantages as well. Like if these solute atoms are mixed, it will try to restrict the motion of dislocation. So how it will restrict the dislocation? What can happen if dislocation is moving with velocity v? The solute atoms will also try to move with velocity v dash, where it will try to achieve v dash more than v, so that the solute atom can sit in front of the dislocation and the dislocation motion will be hindered. What will happen? The hardening will take place. So what happens in case of atmosphere? When we increase the strain, the dislocations move, the solute atoms also move. But if somehow we apply some external temperature increase, the dislocations and the solute atoms both feel a favorable condition to move very faster. But if we increase the strain rate, then what will happen? The strain rate has been increased, means the strain is taking place very fast. At the same time, due to that fast elongation in the material, the thermal some temperature also rises. So the temperature will also rise, and as a result, this will act as a thermal activation for the solute atoms. For the solute atoms. So these thermal activation will help the solute atoms to move faster than the dislocations. And what will happen? Due to the higher strain rate, the dislocations will not get enough time to move, but the solute atoms will have, and the solute atoms will sit in front of the dislocations. At that time, if the solute atoms are having a very high affinity towards each other or attraction force between each other, then they will form a second phase precipitate. Means they will form a grain which consists of the solute atoms only. So in the other grains, out of the other grains, one grain will be seen where a lot of alloying elements are present, and they have formed some compound. If this is the precipitate in the TEM analysis, if you see this is the precipitate, means this grain is having a lot of alloying elements. The alloying elements are uh, have formed some compound or intermetallics, means some compound with each other or some compounds with the parent metal, and they are bonded with each other. They are making some separate lattice there. So that will be considered as a precipitate. But if they are not having that much or enough attraction force between each other, then what will happen? They will just sit bonded with each other but not a compound. They will make a cluster. So that will be called as atmosphere, which is a cluster made of solute atoms. These solute atoms can be only B. These solute atoms can be B, C compound, can be B, C, D, and etc. All the alloying elements. This B, C, D, E, these are the different alloying elements which has been added to the aluminium. So when the motion of the dislocation is hindered by the solute atoms, so dislocations are also nothing but an atomic arrangement. So if they are now sitting together at a place, then there will be a stress develop in between these dislocation and solute. When the dislocation moves away from the solute, tries to when one dislocation tries to go away from the solute, the stress increases. But after some time, the stress decreases and the dislocations are free to move further away from the solute atoms. So the stress developed between those two are called drag stress, and in there is a dislocation velocity. So as the velocity increases, as the dislocation tries to move further away from the solute, this drag stress increases. After a certain point, it will decrease. After attaining some critical velocity, also some critical distance from the solute atom. So yeah, this was the graph, but this graph also depends upon the temperature. If the temperature increases, then there will be effect on the critical velocity and the velocity and the drag stress. So the critical velocity has been shifted. So strain rate is also having a significant um, effect on this atmosphere and the dislocation movement phenomenon. After that, solution hardening. So this is the solid solution hardening, means we are not applying any temperature here, we are not applying any stress, we are not doing anything, we are just mixing the alloying element, and due to the mixing of alloying element, the alloying elements are serving their purpose of alloying, means they are hardening the material with different aspects, but that hardening value will not be that much. So to increase the hardening value, we do some artificial things. Means externally we apply some strain, means externally we apply some load, or externally we increase the temperature, we hold the temperature, or we increase the temperature and the load as well. So these different varieties of things we do to the alloy to harden it more. So the next point is strain aging. What do you do in strain aging, anyone?
Ma'am, like we apply a certain strain and then we leave that material for some time and then again we start applying stress to it. So what happens is like when some dislocations are formed, if we are leaving that material in that state, the solute atoms will be pinning those dislocations, and next time we will apply stress or external load, then my yield point will increase.
Yes. So whenever we are adding some what say this solute atoms, so they are having some effect. But apart from that, if we are applying some strain, we can harden the material. So in the last class also, there we see when we apply some external load to a material, it deforms. But there can be two phenomena. Those two phenomena can be simultaneous and are opposite as well. Means there will be cross section reduction if that is a tensile stress. The cross section reduction will lead to the less sustainability of the external load, but at the same time, due to the strain, if there is some strain aging or work hardening, then it will increase the hardness of the material. So these are two opposite phenomena. So here we are considering the work hardening part only. So work hardening means when we are applying the strain, the dislocations are difficult, are feeling difficult, finding difficult to move further. So as I already said, if you increase the strain rate, the dislocations will not feel easy to move. So that is one type of strain aging. Then if you to apply some strain, you wait, after some time you again apply some strain, there will be the movement of the solute atoms, and there can be solute atom buildup at a particular stage, which will lead to the hardening. Then these are the phenomena where at the stopping time you are having some hardening effect. But these same things, if you get at the time of deformation, that will be called as dynamic strain aging. Aging means whenever we hold the material at a particular uh, point with some process parameter value, that is called as aging. So in strain aging, we strain the material, we age it means we hold it for certain time, then again we strain it. And at the time of aging, at the time of holding, we are basically we are getting some increased value of hardness. But if at the time of straining we are getting some increased hardness, that will be called as dynamic strain aging. So there is one another story of Cottrell Bilby theory, where it was said with a diagram that in which path the solute atoms go and in which path the dislocations go. Always remember, all the things are moving inside the material to get a stable position. Why do these dislocations move when we elongate the material? Because when we elongate the material, when we applied some external stress to the material or external load to the material, the energy of the material increases, the bonds get started vibrating, they try to stretch, the bonds get stretched, and the energy increase. So to minimize this energy of the whole system, to get a stable point, to get an equilibrium inside the system, the dislocations start moving. So the ultimate goal or motive of the dislocations to get are to get a stable position. The solute atoms are also going. Why? The solute atoms are trying to catch up the dislocations because that is their stable position, that is their motive. So all the things are going because to get a stable position. So obviously all the things will always go from a high energy zone to a low energy zone. There will be a energy gradient always whenever you are applying some load, because we never apply the load throughout the material. At a certain point we applied the material load, and from that point the rest of the material experience the load. So due to which there will be a energy gradient, and towards the low energy from a high energy all the things go. So there was a picture related to that. Then the dynamic strain aging part is coming. So there is serration. So why serration happens? As I said, so whenever you are increasing the strain rate, what happens is up to this point, I said in the one of my classes also that Up to this point now, the material is considered as a perfect material or lattice with no dislocation. Up to this point, the strain can be recovered. So up to this point, the dislocations are, means there is some formation of dislocation to accommodate the strain inside the material. So up to this point, there is formation of dislocation to accommodate the strain applied. After some time, up to Hooke's law, whenever you release the load, the strain will be recovered, the material will go at its original shape and size. So that is the phenomena. After Hooke's law, what happens? The dislocations doesn't get demolished inside the material. So the dislocations will still be there, but the strain can be recovered. But at upper yield point, that is the phenomena up to upper yield point. After upper yield point, what happens is dislocations will also get forming, and the strain will also get introduced, means there will be elongation in the material which will be like plastically, it cannot be recovered. And at that position, what happens inside the lattices are, as the strain is increasing and the strain rate is high, so the dislocations are formed, the solute atoms are trying to catch up, the solute atoms are catching up the dislocation, because the number of dislocations are low. So it will happen till this point. And after some times, what will happen? The solute atoms cannot restrict the dislocations anymore, because there is now a lot of dislocations rather than the number of solute atoms, and the strain is so high that it's having a favorable condition for the dislocations to move. So the dislocations will move with higher velocity, the solute atoms cannot catch it, so the strain will increase. After some point, after necking, it will go down, means it will meet the fracture. So up to this point, is it clear?
Yes, ma'am.
Okay. So this is the phenomena of dynamic strain aging, and due to this portion, there will be serration. Serration means the solute atoms are going, dislocations are going, solute atoms are restricting the dislocations with each movement. So there will be a shear band present over the gauge length of the material if the material is exposed to the tensile testing. And if this is the tensile sample, in the gauge length there will be some serration, so there will be some lines like this, and it will be called as serration. It will be shown, it will be observed through naked eye as well in the tensile sample after the test. So after that, there is a PLC effect. What is the full form of the PLC? Portrait La Chatelier effect. So this is nothing but the sedation, what is happening, which is happening due to the shear strain, high rate, and this movements. After that, we got to know about the dynamic strain aging, that the dynamic strain aging was continued, that the thermal activation and the applied stress both acts important or have an important role in the overall activation of the solute atoms and the dislocation as well. Whenever the DSA is happening, means in the high strain rate, we are having the hardening effect without any aging. So which is not good actually, because we have an estimation that for this much strain will have this much hardening, but due to the serration, if we are having much more hardening, that then this is not in our control, and which is not in our control, that can never be repeatable and reproducible. Means whenever you are working with a material, now you have gone up to certain limit of temperature and time, and you are having sedation, and due to sedation you are having hardening effect. But when I will be doing that work, didn't if I don't go up to that temperature and time, I'll have, or I'll expect to have a proportional hardening effect inside the material, but I'll not have that proportional hardening effect, because you got that hardening, that very high hardening effect due to the problem that arised into your material, which is called as sedation. But I won't have that sedation because I didn't go up to that temperature and time. So the process, it's not reproducible and repeatable. This is why we always want to avoid the sedation. We want to avoid the DSA, although it's beneficial for us as we are trying to get some hardening and it is giving us the result of hardening. But we always try to avoid that. So what we do, we avoid that time and temperature value in which a particular material show the dynamic strain energy. But for aluminium, actually it has been seen that for normal temperature also aluminium shows the sedation because of the magnesium and silicon, all those alloying elements present over there. So there were three types of sedations, type A, B and C, where there was like the dislocation is localized, or there are some disappearance of the shear bands and initiation of the new bands, or there is some continuous sedation and no propagation of the sedation band. So depending upon those things, the type A, B, C was demonstrated. After that, uh, there is the inverse behavior. Yes, inverse behavior observed when the strain rate is increased. Then there are some different types of dislocations. Yeah, and then the precipitation hardening started. So if you have any doubt till precipitation hardening, then you may ask. Otherwise, I'll then start with the precipitation hardening.
Ma'am,
Yes.
what do we exactly mean by when we say velocity of any dislocation? I understand like along the glide plane it is moving,
Yes.
but when we say that the velocity of edge dislocation is greater than the velocity of screw dislocation, so ma'am, do you get what I mean to ask?
Yes, yes, yes. So it's like you see, there are two types of dislocation. If you understand that what is the difference between these two, then you'll understand why then you will be the person who will answer like the edge dislocation will always have more velocity than screw dislocation, because edge dislocation is very simple. It will have a this type of uh, arrangement, this extra half plane, which can glide just in the forward direction by just making some bonds. But in case of screw, it's going one plane to other plane. In screw dislocation, it moves like this is edge, but this is screw. The screw is changing the plane. So when it is changing the plane, it has to interact with the other plane. So even if it is going from one parallel plane to other parallel plane, but when it is changing the plane to move forward, it has to interact with the plane which is at a perpendicular direction with the parallel plane. So if this is the first plane, if this is the second plane, if this dislocation is moving like this, then it has to interact with the plane which is sitting over here also, which is perpendicular 90 degree to the parallel to this plane of the slip plane. So it is changing the plane. So obviously it needs higher energy, because you know that the property of each planes are different, and the parallel planes of also always have similar type of energy and property, and the perpendicular planes have very different energy and property. So it has to interact with the very different energy level to go to the next parallel plane. So obviously it needs more activation energy. This is why its velocity is less, means it needs more time to go in the second plane and in the next plane and in the next plane. This is how it will glide or it will cross slip. So this is the phenomenon. Is it okay?
Yes, ma'am. Yes, ma'am.
Okay. So now let's start with the precipitation hardening. If you don't have any other doubt, I think. If yes, you can ask.
No, ma'am.
Okay. So precipitation hardening means, see, when we mix the sugar in the water, we want the sugar to be dissolved in the water fully. We do not want to sit we want the sugar to sit at the bottom of the water. Whenever we mix some sugar in a tea, we stir it with the help of spoon until unless the sugar is properly mixed with the tea. And also, uh, we ensure that there is no excess sugar. At the same time, there is no sugar deficiency in the tea. uh, let's assume that you are not a sugar patient, so you will have a you will like to have consume a minimum enough amount of sugar in your tea. So we always ensure that there is proper amount of sugar but no excess sugar. So what we do we stir the tea with the help of spoon unless until the sugar is properly mixed with the tea. So this is what happens in case of solid solution also. We stir the solid solution by some other means to get a proper mixture of the alloying element with the parent metal. When we do alloying, we generally cast it or we powder metal. We take the help of powder metallurgy. There also we mix the powder using ball milling. So our main motive is to mix the alloying element properly with the metal, and at the same time we also want that the alloying element should be soluble at the room temperature as well. When you mix some sugar and salt inside your water to be hydrated, to take it for your hydration, you do not heat up the water. For in normal condition, you mix the sugar and the salt in the water and you stir it, you mix it. You ensure that there is no excess amount of sugar and salt and there is proper amount of sugar and salt. We mix a little extra sugar than salt. The amount of sugar is more than salt because that tastes good. The same things happen in case of alloys also. For example, in case of 5000 series alloy, we mix a little more amount of magnesium than silicon. We mix both. We mix magnesium and silicon as well, but we mix more magnesium than silicon to get the proper taste of that alloy depending upon the application. Here the application is hydration of our cell, for our cell. There the application will be something different, but we want a proper mixing. Then what is precipitation? I have shown that precipitation means some alloying elements are making some compound or intermetallics in between each other and they are sitting over a particular position and they are just making some clusters. There will be a grain which will consist of that alloying element only. But this should not be the case in case of solid solution. Then why we are taking help of such precipitate? Because whenever we mix some alloying element in a solid solution, we ensure that the strength of those alloying elements are more than the parent metal, so that we can get that hardening effect. So we want that solute atom should have a good solubility inside the solid solution even at room temperature. because when we make it, we take help of casting. Casting deals with the melting point of all the elements. Now, at the time of melt, when the things are melted, they will mix because we'll stir it. In a stir casting, we'll stir it. But when it is solidified, it should not be the case like all the alloying elements are making some precipitates. Then our purpose will not be served. So this is why we always want the solute atoms to have a very good solubility even at room temperature, and the solubility should increase with the temperature, with the ambient temperature of that solid solution. But again, we are going for precipitation hardening. We are opting for the precipitations. We are doing some phenomena, taking help of something which will result in the precipitation for the hardening effect. But do not consider it as like we will mix the alloying element in such a way that it will form the precipitate at the time of casting, so we'll have the hardening effect. No. So how we can achieve that precipitation? So we can go for heat treatment processes, different heat treatment processes. So there are the designation for heat treatment as well. So there will be T1 to T10. T1, 2, 3, 4 to T10 type of process where you'll get different type of hardnesses. T6 gives us the peak hardness. Deals with the artificial aging. So again, next concept which is aging. So the next phenomena which is coming into the picture is aging. So at the time of strain also, strain hardening also, we are taking help of strain aging. Here for heat treatment, we'll take help of normal aging, where we'll hold the material at a certain position with a certain time, for a certain time and with a certain temperature. So quenching, normalizing and annealing. Tell me the difference between these three.
Ma'am, I think quenching is when we cool at a very fast rate from higher temperature in order to regain the high temperature phase, in order to retain the high temperature phase. And annealing is when we when we go above the solvus temperature line or the upper critical temperature line. And ma'am, what was the third one you asked?
Normalizing.
Yeah, normalizing is when we do air cooling. It is like in annealing, it is more of a furnace cooling,
Yes.
cooling at a very slow rate or at near equilibrium rate. And normalizing is like cooling at a rate which is between that of annealing and quenching.
Yes. So normalizing deals with air cooling, annealing furnace cooling, and quenching rapid cooling. So for quenching, it's pretty easy. For quenching, we'll just quench it. The grain refinement will take place. So there is no need of other things. There will be hardness. Huh? But for annealing, there is furnace cooling. So there is sufficient time for the grain growth. So the hardness will be not that much. But for annealing, what we can do is we can we cannot expect the grain refinement or the hardness out of annealing. But after annealing, we can do some other processes. So we basically do annealing to increase ductility. Okay. So we'll not be talking about annealing here. For normalizing, it's air cooling. Again, it's very slow cooling. So there will be grain growth and the ductility will be maintained. You can say the hardness will not be increased. So we'll be not talking about normalizing as well. So we'll be talking about the quenching. So in case of quenching, there will be very rapidly, very fastly. There will be no time for the grain growth. When the metal will be solidified, it will be just solidified as it is. The grains will be formed, but it will not get enough time to grow. That's why we get some grain refinement out of this type of quenching process. But after the quenching also, we can go for some stress relieving process, or we can go for some shaping process like the forging or forming, or we can go for some aging process. What is aging? It has been observed that when you keep the material for longer time, the hardness increases. Now, if it's at higher temperature, it will be called as artificial aging. If it's at lower temperature, it will be called as normal, normal aging or natural aging. So, what is the mechanism of hardening out of this aging process? Can anybody tell me what really happens at the time of aging? What happens at the time of aging?
Ma'am, actually, my internet got lost in between.
Okay.
Can you repeat the question?
Okay, the question is what happens at the time of aging?
At the time of aging, since we did quenching, so we formed a super saturated solid solution. So when we age, we basically allow the solute atoms to cluster together,
Yes.
like they come out of the matrix.
Hmm. So what happens is when it's a normal water, we can mix a optimum amount of sugar into it. But when it is hot water, we can add a lot more than the optimum value of the amount of sugar. So that's what we do here in solid solution. At the time of casting, what we do, it's melted, it's heated up position. So we add a lot more number of solute atoms or alloying element inside the metal alloy, and to make it super saturated, means which is more than saturated. And when we cool it down, after cooling it down, when we are doing slow cooling, the excess amount will be what say the excess amount will be come out as a will be coming out as a rejected material. So the solid solution will reject the excess amount and it will form the clustering, but we don't want it because that will not be very distributed. So what we do, we quench it so that we can get the supersaturated solid solution at the room temperature, and then we hold the material for some time before going into the next processing. So that holding time is called as aging. If it's at room temperature, it will take a lot of time, lot of days you can say, or months. But if you are holding the material up to certain point, up at a certain elevated temperature, the aging will go faster. What basically do happens at the time of aging is the excess amount of solute atoms which were mixed at the time of solid solution preparation will be rejected, or not will be rejected but will form the precipitates. It will form the clustered precipitates, and due to which the hardening will take place. So first of all, it will uh, make some clustering, which will be called as GP zones. Then these GP zones will try to match their lattices with the parent lattice, will try to maintain the coherency just to get an equilibrium position. Whenever the equilibrium position is achieved, the aging will be stopped, but naturally it doesn't get stopped. It will further continue its aging process and it will be overaged. means the ductility will again be increased. So what happens? First, there is a supersaturated solid solution. Then you are quenching it. So it's supersaturated solid solution at room temperature. Now you are doing the aging. So the GP zones will be formed. Now these GP zones to try to maintain the coherency, the lattice mismatch, try to reduce the lattice mismatch, and its ultimate goal is to achieve the equilibrium position so that it can have a and stable condition inside the material so that it can sit peacefully there. So after attaining the stable condition, which is the equilibrium, if you hold the material for further time, then it will be overaged, means it will further grow, and due to the growth, the distance between the growing or grown up particle will increase, and in between them the dislocation can move again, so the ductility will increase. So this is the here the aging is done, so it is having the perfect hardness. But after that, if over aging is done, then the ductility will increase. So this is the phenomena of the aging process, natural aging or artificial aging. Now natural aging is done at room temperature, but artificial aging is done at elevated temperature. Then all the phenomena behind this aging process, like the stacking fault energy is related, the coherency is related, the ordered structure is related, the modulus effect, interfacial effect, lattice friction, all those things were there. The most interesting fact was, if there are some precipitates sitting like this, the dislocation will try to go in between this precipitate, but these precipitates are growing, so it will not get sufficient place to go in between them. There are other precipitates as well sitting over there, but I am considering this one dislocation only, which is trying to go in between these precipitates. So what will happen? It will go like this. It will try to go like this, and as a result, when it will pass, there will be some portion of the leftover dislocation there, and that leftover dislocation will sit like this, surrounding the solute atoms. But if you this dislocation will go, but if you do the overaging, this solute this clustering or precipitate now will grow. So what will happen? It will grow, and the distance between these two, if it's lambda, this lambda will increase, and as a result, if this is the precipitate, now this dislocation can move very easily through the in between portion of the two precipitate. So this is how for overaging the ductility again increases. Then uh, yes, precipitate sequence is also important, how it is forming. So it's like for 2000 series it was theta. For 2000 series it was theta, theta prime, theta double prime, theta prime, then theta. For and the precipitate was CuL2, I think. For 6000 series it was beta. It was beta, right? For 6000, or what? You can also tell me. You can
Ma'am, I need to check. I think it was eta or I need to check, ma'am.
okay, okay, no problem. It was beta prime, then beta. So it was beta. So first supersaturated, then GP zones, then these things. For 7000 series, it was eta. And so it was Mg.
For 6,000 it was beta and 7,000 it was eta.
Yes. And for 8000, it was gamma, I think. Sorry, delta. Then it is delta, and the precipitate is Al3Li. Here also two types of precipitates are formed. Depending upon the percentage of Li which is present over there, the precipitate will be formed. So if the force is much more, or if you are doing artificial aging or natural aging, but if the dislocation still tries to go overcoming this barrier of the solute atom, it can happen that with the solute atom will be broken, but if it's broken, the surface area will increase, which will enhance the surface energy. And if the surface energy is increased, means again the dislocations cannot move further. It will feel more difficult to move further. So the dislocation is making some barrier to its own path only. So these were the phenomena for the precipitation hardening. So you can do the cold working as well for strain aging. For precipitation hardening, the precipitates are now there. But if you want to go for grain refinement, then you can do some cold working. There you basically elongate the grain, or you can just order the grain. So there also you can get some hardening effect. And that hardening effect you can do for heat treatable and non-heat treatable, both the alloys, because for non-heat treatable the precipitates will not be there. Some clustering may be there, but not the precipitates. So therefore you cannot go for this aging. You can, in that case the clustering will be formed, but if you want more hardness, then you have to go for the forming processes, where you can do the grain refinement by grain elongation, or making some smaller grains. So there are again nomenclature for non-heat treatable alloys as well, which are denoted as H, F, O, etc. Which temper condition is it in? Depending upon that. Then there was the dislocation density. Why we are concerned about this dislocation density? Because when we go for cold working, now cold working add a lot of dislocation, million trillions of dislocation, then dislocation in the material, means a lot of dislocation will be introduced in the material. Dislocation density will be very high. Now the dislocations, when the dislocations are moving inside the material, we get the ductility. But here, even if we are adding, we are introducing a lot of dislocation, but here we still uh, we are able to harden the material. How? Because as the dislocation density is now so high, that all the dislocations, they will interact with each other, and they will restrict their own movement. They will be arranged in some position, and they can do many things one by one. First is the cottral barrier. So there will be some already present dislocation, there are some newly formed dislocation. Now these both type of dislocations will interact with each other, and as a result they will find difficult to move further, which will be called as cottral barrier. So there was the jocks and kings. I have already discussed this jocks and kings in the last to last class, so I'm not discussing it again for the time. Then, due to the jocks and kings, so the dislocations were broken down into two pieces. So obviously the density is now again increased and it will interact with each other and it will not move. It cannot move further. This is one phenomenon, jocks and kings. The other which can happen is due to the rock hardening, as the density is very high now, the dislocations can the ultimate motive of the dislocations are to get a stable condition. So now as the density is very high, to get a stable position, what they will do, they will clusters themselves. So they will arrange themselves. Dislocations arrange themselves. So what is the result? They will form some cellular structures. They will form some structures like this, and it will see exactly this type of picture inside the grain in the SEM or in the EBS. Some very black portions like this, which signifies that the dislocation density is so high that they are making some cellular structures by themselves, by arranging themselves. So which can be the next, the second phenomena. So piling out of the dislocations. So now if the dislocations are piled up, then the next thing which can happen is the recrystallization and recovery. So two things can happen. If the dislocations can somehow move further, they will increase the ductility, which will be called as recovery. But if the dislocations are so high in density that they are helping the grain to refine, means they are helping the grain to form new bond grain or new strain free grain, then it will be called as recrystallization. So what happens that high SFE, the cross slip will occur, this location piled up. Then if the SFE is low, then the dislocation cannot move further. So there, some using some different phenomena, the grain refinement can take place. So the first thing is polygonization. So we are starting the recrystallization part. The first phenomena is polygonization, where the dislocations arrange themselves at a particular manner. If they are opposite in nature, then it will form a continuous line. If they are same uh, structure, then they will pile up like this, which will be called as polygonization. The next thing is, if there is a grain in which if there are two grains in which the dislocation density is very low and here the dislocation density is very high, what can happen is there can be a bulge created at the grain boundary, and due to which the dislocations which are present over here, it's very high density and here it is low density. So the dislocations will get arranged in this position. What will happen? And as a result, this portion will be strain free. strain means I have discovered strain means dislocation. So this portion will be dislocation free. As a result, now we have a grain. So this is now grain 1, this is 2 and this is 3. Previously there were only 2 grains. Now there are 3 grains. So grain refinement, or not, if not grain refinement, then new grain bond, which is strain free. So which will be called as recrystallization. So these are the two processes by which the recrystallization may happen. There can be others as well. For example, can you name other process, one other phenomena by which recrystallization may occur?
Ma'am, other phenomena means
Uh, okay. Next, I can say like if there are, I think he is having some net issue. Let him join. Then I.
Ma'am, am I audible?
Yes, yes.
Ma'am, like, I didn't hear your question, ma'am.
Okay, these are the two phenomena by which the recrystallization may occur. Means by which we can have a new strain-free grain. So can we name any other process by which new strain-free grain can uh, occur, can form? Other phenomena like this phenomena which I have discussed. One is polygonization, another one is grain boundary bulging, the third, fourth, fifth. Any one
Ma'am,
process?
like, in this one only once like bulging happens, like grain formation correlation can happen with that.
Huh. Then next, can you recall one thing where there was subgrain formation by grain rotation?
Yes, ma'am. Subgrain formation by grain rotation.
Yes. So what happens there? So if there is,
Ma'am,
yes,
when two grains are attached together, there was like this grain boundary that was there. So I remember that it was getting increased, and there was some rotation such that the misfits are reduced and a big grain is formed.
yes, exactly. So it will rotate in such a way that after some time there will be no mismatch between the lattice orientation of this two grain, and if this mismatch is less than 5 degree, then it will be called as one grain. So this was one phenomena by which the grain, this rotation can give rise to this type of nucleation. So recrystallization means nucleation of new grains. Now, so here out of the old grains, we are making some new grains. Nucleation can be by other means as well. We'll see. But this time I am discussing about the nucleation out of the old grains. So the next phenomena can be if there are some grains, if there is a grain which is having three faces, there all the faces will this make it larger.
Excuse me, ma'am.
Yes.
Ma'am, actually, I had a doubt in the class we had taken this also, and when I revisited the lecture, in that I remember sir was talking about low angle grain boundaries
Yes.
in that subgrain formation. Ma'am, this can only happen for low angle grain boundaries, isn't it?
Yes. Yes.
Okay, ma'am.
Because low angle grain boundary means the grain boundary misorientation is less than 15 degree. Okay.
Yes,
So
ma'am.
then only after rotation it can have that less than 5 degree. less than 5 degree. If it is more than 15 degree, na, it will need a lot of rotation that cannot be sustained by the grain. So only if it's low angle grain, there is a low angle grain boundary, then only it can happen. So the fourth phenomenon is if there is a grain which is having three faces, then due to the low energy, it will try to get demolished. So after some time, it will disappear. But if there is a more number of faces, it will try to grow, and out of which the nucleation may take place. So it is more like growth, it will disappear. But if it's more than six phases, then it will try to expand its phases, so growth will take place. There are some things. Then these are the typical types or variety of phenomena which really take place for the new grain formation or recrystallization or nucleation out of the old grains. After nucleation, the growth will take place obviously, but it depends, means if these are the phenomena, these are occurring in some elevated temperature or at room temperature, actually some elevated temperature, not that much. But if you increase the temperature very high and then you cool down slowly, then the growth will be more, so there will be more growth. Other than that, the recrystallization can be dynamic recrystallization as well, means at the time of deformation if the recrystallization is taking place. So before these recrystallization up to this 4 point, it's static. Now we are going to talk about dynamic. In case of dynamic recrystallization, what happens at the time of deformation? In static recrystallization, due to the deformation, as the dislocation density has been increased, so now due to the high dislocation density there are some recrystallization. But here at the time of deformation only, recrystallization is taking place. So it can be CDRX, GDRX or DDRX. DDRX, CDRX and GDRX. Okay. May I know that in which year are you in currently, Vanshika?
Mom, I'm in third year of my college,
BTech.
BTech.
Okay, okay. So these things will be useful for you in the future also if you are going for higher study. For as of now, I don't know how much it is useful, but yeah. So for
Yes, ma'am.
DDRX, DDRX is less uh, or DDRX results in lesser grain refinement than CDRX. So in DDRX, what happens is at the grain boundary, by grain boundary bulging, a new grain can be formed. In case of CDRX, due to the interaction between the all low angle dislocations or low angle grain boundaries, the strain, the shear bands occur, and out of the old grain, some new grains form, and due to which the grain refinement is more distributed and more in number. This is one thing. And then GDRX is due to the geometry of the product, means if you are going for rolling where a lot of dislocation density has been increased, so as the dislocation is lot in number, so if the serration is happening, the grain boundary serration will happen. So due to the grain boundary serration, if the serrations touch each other, the serrations will make some new grains. So out of the serrations, the new grains will be formed, and which is known as the GDRX. If this is the serration, if it touches, then there will be two grains out of one. So these are the difference between the uh, difference between DDRX, CDRX and GDRX. If you have any specific doubt, you can ask. Otherwise, I will go to the next topics because less time is left.
No, ma'am. We can go to the next.
So next is the grain refinement. This is the recrystallization, make formation of new grains. When new grains form, it will be smaller in size. But here in CDRX, out of the old grain, some new grains are forming inside it. So the grain refinement is also taking place. Grain refinement means the grain size, I am making some smaller grains out of a bigger grain. But for DDRX or GDRX, the grain refinement doesn't occur at the time of dynamic recrystallization. We have to go for some further processing. So according to Hall patch equation, when the number of grains increase, that will be grain refinement, called as grain refinement, and it will increase the strength of the material. So the number of grain boundary will also increase. As the number of grain increase, so the grain size decrease. So this is what we do at the time of grain refinement. What we can do, we can uh, appreciate or we can describe the nucleation process in various way in which the grain refinement can be discussed. So first is if you are doing the quenching. In quenching what happens? Out of the melted material, suddenly the whole material will be solidified. So all the grains, all the metal crystals or metal lattices, metal alloys which are present over there in the melted condition will be solidified. So whatever is the lattice structure at the time of melting, that will be solidified as it is. So obviously there will be very high mismatch between the lattices over there, because melting means the distance between the atoms has been increased. So obviously the grains will be very smaller, because at a very smaller portion you can find a similarly oriented lattices, because grains are basically similarly oriented lattices form a grain. So this is why the number of grains are more, because the grain sizes are very small. So at the time of quenching you can do the grain refinement. Other way, in case of casting, you cannot do the quenching. What you do? You do some other phenomena to have the nucleation. The nucleation can be homogeneous or heterogeneous. Homogeneous means out of no help, without any help, the one grain is forming at the middle of the melted material, and as it is forming, so it will be spherical in nature, it will be small, and in the whole metal there will be small grains formed. So out of nowhere, without any help, some grains are formed, and as these grains are formed like this, however I am drawing, the grains are forming like that without any help, it will be called as homogeneous. It will be evenly distributed, but it doesn't occur. It is rare, because it's not possible now, without any help of anything the grain is forming. It is not possible. What is possible? That is heterogeneous nucleation, where with the help of some other material the nucleation is taking place. Means if it is solidifying means the temperature is decreasing, but at the time of casting na, the temperature decreases very slowly. So what happens, this mold wall is cooler, so with the help of mold wall the material will start solidifying, and with the help of the, if there is high temperature gradient there can be dendritic structures. With the help of dendrites, if some dendrites are broken down inside the melted region, then those broken dendrites will act as a nucleating site. With the help of these solidified grains some other grains will be solidified, and if there are some new inclusion inside the material which is not solidified, with the help of that nucleation some grains will be solidified, and in this manner the solidification will take place, which is more often. This is why the heterogeneous nucleation is not that much distributed, well distributed. This is why it's called heterogeneous, but it is the natural phenomena which happens often. So as I said, it can happen, it can occur by many way, due to the temperature gradient, with the help of mold wall, dendritic walls, or inclusion, etc, etc. So the melt inoculation is also one technique where I said some Ti particles you can add in the aluminum. You can consider it as a Ti particle that you added inside the alloy, so that the Ti will not get melted because the melting point of Ti is much higher. So that Ti is a solidified particle inside the melted region, so the Ti will help the melted aluminium to get nucleated. So this is how, if the Ti makes some intermetallics, then the intermetallics is having some facet, and those facet will help in the further nucleation. And this is how the different types of grains are formed. It can be equiaxed, it can be columnar, it can be small, very small and well distributed grains, but it's not possible anyhow. The homogeneous nucleation gives us the equiax grains all over the material, all over the mold, but it's not the often case, it's not possible, it's very rare. So in case of casting, at in the mold world there will be equiax, then there will be columnar, then there will be some irregular shaped grains. So these are the things. Then the dendritic structure was introduced. So this is all about the heterogeneous and homogeneous nucleation. There was other part of the homogeneous and heterogeneous nucleation as well. This is a broad spectrum. Then in dynamic recrystallization there was the another part which is severe plastic deformation, which is again very interesting topic, in which we are applying some external load, some stress, but we are not increasing the material length, which is known as the severe plastic deformation. We applied a high load, very high F, but no deformation in real sense. But in terms of metallurgy, there will be a lot of strain. Lot of strain means a lot of dislocation, but there will be no physical deformation or elongation. So this is how we increase the number of dislocation and we strengthen the material. Then the metal matrix composite was started. It's new to us, I think. In the last 4 weeks we are discussing about metal matrix composite, so it's not important to, it's not necessary to discuss this thing again. But anyhow, if you have any further doubt after this recap class, you can ask me in the next class, which will be the last class. Also, if you get if you got any help from this whole lecture series out of this 12-week doubt clearing session, you can help me in my TA by just submitting the feedback form. Also, if you have LinkedIn, you can just post a small thing. You can follow me on LinkedIn and you can tag me there in your post if you get any benefit out of this course. It will help in my further TA. So I think that's about it in this class because the time is also finished. So if you have any doubt, I'll clear it in the next class. You just write it down. You can mail me. You can text me over LinkedIn. Anything I'll discuss in the next class.
Sure, ma'am.
Okay, so now then we can stop the class here. I'll upload this slide, whatever I have written in the drive so that you can see. Okay, so let's start.
Also, ma'am, I got a small request from my side.
Yes.
Ma'am, is it actually possible to somehow get the past year questions for this course?
Which question?
Ma'am, past year questions of the final paper. I just wanted to see.
Oh, final paper last year question. I think I don't have.
Okay, ma'am.
Only
Although,
the
ma'am,
12 weeks questions I have for the last year that I have already included in all the slides. If you see in
yes,
everyday
ma'am.
slide, no? So the final exam paper I don't have.
Okay, ma'am. I'll go through those questions that you've given.
If
Thank you.
I get from somewhere, I'll send you through that. I'll make a PPT of that question paper and will upload it in the Google Drive. In the meantime, you can just practice the previous year question for the respective weeks.
Sure, ma'am. Thank you,
Okay.
ma'am.